Solving Indian Forest Services Mechanical Engineering Paper 2 of year 2024. Question number 7A is the power output of a Francis turbine is 1100 kilowatt at an overall efficiency of 90% without using any draft tube. The available head at the inlet to the turbine is 26 meter and the level of turbine is 2.3 meter above the tail race. The flow coefficient of the turbine is 0.3. Assess the effect on power output when using 1. A straight cylindrical draft tube and 2. A draft tube with half cone angle of 5 degree at the exit of the turbine. The efficiency of draft tube in both the cases may be taken as 94%. The atmospheric pressure head may be taken as 10 meters. First of all, considering without draft tube. So when we consider without draft tube, then the power is given as 1100 kilowatt. Overall efficiency is 90%. Head at inlet is given as 26 meters, and the level above the tail base is 2.3 meters. So the net head available for power production is 26 minus 2.3, that is 23.7 meters. And we know that the power is rho QGH into overall efficiency. H is H net. H net is 23.7. Rho is 1000 per water. G is 9.81. And overall efficiency is given as 0.9 and power is given as 1100 kilowatt. 1100 into 1000. So from this we can find out Q. So Q is your discharge. Discharge comes as 5.256 meter cube per second, and the flow coefficient is 0.3. So from the flow coefficient we can find out flow velocity, which is constant, and in case of Francis turbine, the flow velocity at outlet is equal to absolute velocity. So flow velocity is 0.3 into root 2g h net. Okay. So it comes out as 6.469 meter per second. Okay. So now this is your, we can say, exit velocity of the turbine when there is no draft tube. So when there is draft tube, then this will the water will enter with this velocity in the draft tube. So if the draft tube is straight, then the velocity will remain same. So V2 will remain equal to V3, or it will remain constant throughout. As tail race is above, as turbine is above 2.3 meter of tail race, so that height is 2.3 meter. So that is, this is the entering velocity of, or entering portion of the tail race, and this is the leaving portion. Here the water is discharged to tail race. Okay. So as the efficiency of this tail race is given as 94%, so and velocity is same, so pressure will, ideal pressure will be generated only due to this 2.3 meters. So pressure head, extra pressure head available ideally is 2.3 meters. So if we consider efficiency, so it will be multiplied by 0.9. So it will come out as 2.162 meters. So initially without draft tube the head available was 23.7. Now due to this extra head provided by draft tube, because discharge is now here, not here, the net head will increase. So that will become previous net head, that is 23.7 plus this. So that will be at 25.862 meters. So power will be again rho QGH net into hydraulic or into overall efficiency. So that now H net is 25.862 meters. So power will be at 1200 0.1319 kilowatts. So I'm repeating again. First of all, we will find out H net, that is input and minus tail head above tail race. So that is that comes as 27.7, 23.7, and power is given. So from this power we can find out discharge, and the flow coefficient is given. And from this flow coefficient we can find out flow velocity or exit velocity determined without draft tube. So that is the entering velocity in the draft tube. As draft tube is straight, no diameter variation, so V2 will be equal to V3. So net head increase will be your height of draft tube only ideally, but efficiency is given, so we will multiply it by efficiency of draft tube is given, so that will be, so net head increase will be your 2.162 meter. So previous net head was 23.7, now it has been increased by this amount. So now total net head is 25.862. So power will be your rho QGH into overall efficiency. H is your this. So now the power is 1200.1319 kilowatt. Previously without tube it was, without draft tube it was 1100 kilowatt. Okay. So now second case, when conical draft tube is used, so there is the inlet diameter, there not is outlet diameter, and this half cone angle is given as 5 degrees. So D naught will be your DI plus this part plus this part. So that is this part is 2.3. This is 2.3 sine phi, this is single phi, and this part is also 2.3 into sine phi. So D naught will be your DI plus this part plus this part, that is 2 into 2.3 sine phi. So that is 0.4009. Now we have to calculate DI also, because V2 is known, Q is known. V2 is entering velocity here and Q is discharge. So we can find out DI, pi by 4 DI square into V2 equal to Q. So for from this DI is your 1.0205 meter, and D naught will be your addition of this, that is 1.4214 meter. And now again from discharge, from this equation here putting V3 and here putting D naught, we can find out V3. Okay. So V3 comes out 3.314 meter. Now there is variation in velocity. So here the velocity is V2 and here is velocity V3. So net so head will also be available due to change in velocity. So we apply Bernoulli's equation between 2 and 3, and considering no loss, then here the total head is P2 by rho g plus V2 square by 2g plus Z2, and here the total head is P3 by rho g plus V3 square by 2g plus Z2, and as this is 2.3 meter above, so taking it as 2.3, and Z3 as 0, and here velocity is known, here velocity is known. So P3 minus P3 by rho g minus P2 by rho g will be your V2 square by 2g minus V3 square minus by V3 square by 2g plus Z2 minus Z2, and V2 is 6.4 that we have calculated, and V3 we have also calculated, putting, and Z3 0 and Z2 2.3. So from this we get ideal increase in pressure head as 3.84 meters. Okay, that is ideal, but if we consider draft tube efficiency, then we have to multiply it by 0.94 also, that is the draft tube efficiency. So increase in head is, actual increase in head is 3.61 meter. Now the total head available is previous net head, that is 23.7, and now increase net head, that is 3.61. So it comes at 27.31 meter. The power is again rho QGH into efficiency, so that comes out as H is now this 27.31. Now it comes out as 1267.32 kilowatt.